Hi and good day to Dr. Rafida. We are going to present for the numerical methods BEE32402 and we are from group 5. And for our introduction, which is what is numerical integration actually? It is a system approach used to evaluate the area of volume bounded by intricate geometric path or non-elementary mathematical models where explicit analytical integration fails. Significance in modern electrical infrastructures engineering is power plants and distribution grids does not encounter constant static load. The load variation requires continuous analytical mapping over specific intervals to compute dynamic parameters like total energy delivery, operational, thermal margins, and economic strains. For the numerical integration acts as the operational bridge to process these empirical data logs into precise metrics. And for our problem statement, an industrial factory is evaluating its total energy metrics during a heavy manufacturing cycle across a standard 4-hour shift, T equals to 0 to T equals to 4 hours. The power model is that automated logging instruments approximate the factory's dynamic power requirement using the expression PT equals to T cubed minus 2T plus 4 megawatt. The engineering goal is to find the total electrical energy consumed, E in megawatt per hour. So we have the E equals to T to the T cubed minus 2T plus 4 dt from 0 to 4. The operating parameters constraint intervals domain AB is equals to 0, 4 using a resolution of n equals to 4 identical division.
Hi, my name is Muhammad Defan Abdurrahim. My metric number is DE240115. So in this presentation, I will determine the manual calculation for trapezoidal rule and Simpson's 1 over 3 rule. So the given power function is Pt equal to 3 cube minus 2t plus 4. So to calculate the total energy from T0 to T4, we need to integral first. So it will be the E equal to integral from 0 to 4 uh, to t cube minus 2t plus 4 dt. And then I will show you the trapezoidal rule first. So for the trapezoidal rule, the interval from 0 to 4 is divided into the 4 equal subinterval. So which means the first determine this the H using the formula H equal to B minus A over N. So substitute the value, we got H equal to 1. So next, the function is stabilized by substituting each value to T into the given equation and calculating the corresponding function value using a calculator. So the value that we got is uh, 4, F1 is 3, F bracket 2 is 8, F3 is 25, and F4 is 60. So the sum of the interior value is 3 plus 8 plus 25 equal to 36. So next we substitute the value into the trapezoidal rule formula, which is E equal to H over 2, bracket of the interior value. So we get the E is equal to 68 megawatt hour. Next is the Simpson 1 over 3 rule. So for this method, the same interval and function value are used. So H equal to 1. For the tabulate value are equal to F4 equal to 4, F1 equal to 3, F2 equal to 8, F3 equal to 25, and F4 equal to 60. So we need to separate the odd number and even number. So for odd number is F1 plus F3 equal to 3 plus 25. equal to 28. And then the even number is F2, which is 8. And then we need to apply the uh, Simpson 1 over 3 rule equation. So it means that H over 3, a bracket of total of interval value. So substitute the value, and we get the energy is 64 megawatt hour. And next step is true error and accuracy comparison. So to determine which method is more accurate, the value of the integral must be first calculated analytically. So integrating the function give the Simpson 1 over 3 rule is 64 megawatt hour, and then the trapezoidal is 68 megawatt hour. So we need to find the true error first, which is true error equal to true value minus approximately value. And then the percentage calculation is modulus true error over true value times with 100%. And then so for the trapezoidal, we get the true error is minus, negative 4 megawatt hour. And then for the percentage, we got 6.25%. So for the Simpson 1 over 3 rule, the true error is 0 megawatt hour, and the percentage also 0%. So what we can conclude is the Simpson 1 over 3 rule more accurate than trapezoidal by yielding a perfect zero true error percentage.
Hello and hi, my name is Garrett Ho and my matrix number is BE32402. So today I will present the MATLAB simulation. So in this demonstration, I will verify the energy calculation using MATLAB numerical integration technique. So first, I define the power function at Pt equal to t power of 3 minus 2t plus 4. So the integration interval is from 0 to 4 hours and the number of sub-interval is set to 4. So next, MATLAB calculate the step size h and generate the corresponding time point. The power value at each point are then evaluated using the defined function. For the first method, MATLAB compute the exact analytical integration using integral function. This serves as the reference value for comparison. Then the composite trapezoidal rule is implemented using the numerical integration formula. MATLAB calculate the estimated energy based on the sample data point. After that, the composite Simpson 1 over 3 rule is applied. Since the function is a cubic polynomial and the number of intervals is even, Simpson rule is expected to provide a highly accurate result. Finally, the results are displayed in the command window. So as shown, the exact analytical energy is 64 megawatt hour. The trapezoidal rule gives 68 megawatt hour, which slightly overestimate the result. The Simpson 1 over 3 rules give 64 megawatt hour, matching the exact analytical solution. Therefore, we can conclude that Simpson 1 over 3 rule more accurate than the trapezoidal rule for this problem and is the preferred method for calculation the energy under the given power curve. That's all from me. Thank you.
So for our discussion and error convergence, why Simpson's one-third rule reached 0% error? The error term for the composite trapezoidal method relies on the function's second derivative. The error term for the Simpson's one-third method relies on the fourth derivative. The mathematical cost. Our power model function P3 equals to t cubed minus 2t plus 4 is a cubic polynomial. Differentiating it 4 times yields 0, p, the fourth, t equals 0. As a result, Simpson's one-third rule integrates polynomial up to degree 3 with perfect accuracy. regardless of step count n. In conclusion, the key findings is that both mathematical methods successfully solve the engineering energy usage profile. Simpson's one-third rule proved more accurate than the trapezoidal rule for this curve structure, keeping data processing requirements minimal. Industrial engineering application for a smart grid platform tracking smooth polynomial-like power changes, Simpson's base algorithm offer higher accuracy at low data sampling frequencies. This minimizes real-time microcontroller storage load while maintaining precise tracking for customer billing system.